the classic expanding rectangle, right? So we have an expanding rectangle, who would have thought? And the key part is that its length is 3 times its width. So to represent that, we should introduce a variable. It could be w for width, or x, whatever you're comfortable with. So I'll do x, and I know the length is 3 times that width. Right, and as we increase x, the width, the length will increase proportionally to that, right, by a factor of 3. Awesome. So the area of this would be 3x times x, or 3x squared. Cool. Now the question is asking us, find the rate of change of the area. So rate of change, we should be thinking gradient derivative when the area is 75 centimeters squared. So for a given area, we want to find how quickly it's growing at that specific area. So we know it's increasing, but how quickly is it increasing? Cool. So alarm bell should be ringing. Rate of change, that means we will need the gradient function, right, the derivative. But of what? Well, we want the change of area with respect to its width. So area, width. So we can find the derivative of our area function. So I'll write that as the derivative of area, not with respect to w, we used x, with respect to x. Alright, the first derivative. So 2 multiplies by 3, giving 6, and then we reduce 1 from the power, 2 minus 1, that becomes 1, which we don't need to write. So the derivative of area with respect to width is 6x. Cool. Alright. What else? Actually, what I missed right at the start, which you shouldn't, is whenever you introduce a variable, just say what it means, right? So let x represent width, just so it's clear. Yeah, and then following on from that, we found an equation for the area, and then we differentiated it to find how the area changes with respect to width. Cool. Now, we're asked to find the rate of change of area, so dA by dx, when the area is 75 centimeters squared. So, we have an equation for area, which we can then find at what width that area occurs at. Right, so solving for x. We can then substitute that into our rate of change equation to find dA by dx. So, let's do that now. So, when area equals 75 centimeters squared, we have area equals 3x squared, right? So using our area equation number 1. So solving for the width, divide both sides by 3, square root both sides, plus or minus 5. However, in this case, we'll just take the positive solution. So negative 5 just means it will go the other way, so equivalent. So we found the width when the area is 75 centimeters squared. So now we need to find the rate of change at that specific width. So when width is 5, which corresponds to an area of 75, right? The rate of change of area with respect to width is 6 times the width, which is 30. Awesome. And let's have a think about the units. So change of area centimeters squared per change in width per centimeter. Yeah, so it's increasing at a rate of 30 centimeters squared every time we increase the width by 1 centimeter. Alright, so there's actually quite a few parts of this question, so let's quickly go over it. Firstly, we drew a diagram to represent how length and width are related, so we could then find an equation for the area. Now, using that equation for area, we calculated the derivative, dA by dx, and if we got that far, that is actually an achieved point for this question. We then realize we're looking for the highlighted yellow, right, the rate of change of area, so we needed to know the width. But to get the width x, we needed to use the 75 centimeters squared information. So firstly we solved equation 1 for width, we then use that width in equation 2 to find the rate of change of area. And that would give us our merit component.